Hey guys, I want to talk about something called boundary behavior here. And boundary behavior is when a wave hits another object or hits a new medium, a new material that it's traveling through. So first of all, oh, hey, give me this little laser pointer here. So let's say we have something called a fixed end reflection. So we're going to make a wave over here. What happened in this guy's hand? Anyway, so an end that's tied and not free to move, like a knot tied to a hook or something. So we're going to send a wave here, and we're going to send it down to this end right here that's tied. So what is that going to look like? So, well, let's come here for a second. Let me exit out of this and come here. And let's make a little pulse on this wave. So here is a fixed end. You see that's selected. And they got this rope basically in a vice grip. So we're going to make a wave pulse over here. And boom, we send the wave down and see what happens there. So let me actually turn this damping off here. This damping means it's kind of like friction, means the wave dies over time. So let's try this again without the damping on. So boom, we make a crest and then it comes back. And you see what happens? It keeps getting flipped. So it comes down as a crest, boom, gets sent back as a trough. Comes down as a crest, boom, gets sent back to a trough and gets reflected over and over again. So let's reset that again for a second and talk about why that is. So if you send a crest, think about it like a spring. This rope has tension in it. And as it gets pulled up, the rest of the rope wants to pull it back down. When it gets to this vice grip over here, this fixed in, it pulls up on it. And according to the third law, the vice grip pulls down on it. And if the vice grip is much bigger and stronger, like a knot, it's going to win this tug of war. And it's going to, since it pulls down on the rope, it will send a downward pulse back there like that. So let's come back to here and continue with this. So a little animation, or here is the picture again. So we send an incident pulse, that's the incoming pulse. And let's say we send a crest down in, it gets inverted when it gets reflected. So a crest would get reflected as a trough there, and a trough would have been reflected as a crest. So a few things to note about this reflected pulse here. One thing is the velocity of the reflected wave is the same as the velocity of the incident wave. And that's because it's still in the same medium. And the medium is the only thing that determines how fast it goes. And notice the wavelength hasn't changed. So the wavelength of the reflected one over here is the same as the wavelength of the incident one. And that's because it's in the same medium. Now, most of the time in reality, the amplitude of the reflected one, whoops, it's covering up what I want to point to, would be a little bit less than the amplitude of the incident one because it's going to lose a little bit of energy there. If we wanted to pretend that it was perfect, then those two amplitudes would be equal. But in reality, this loses a little bit upon reflection there. So here's just a little animation of it. Crest comes in, trough goes back. So that's basically what we saw in the other sim. What if we do this though? What if we have a free end reflection? So imagine now the rope, instead of being tied to a knot, it's on a ring here, and the ring's free to slide along this pole. So what is that going to look like when it hits there? Well, let's come back to the simulator here. Let's make it a loose in there. So we're on a ring here, free to slide along the pole, and let's make a pulse this time. Crest comes in. See what comes back there? Let's turn this damping off again. Let's make another crest. Boom, crest comes in. Crest gets sent back. And you can sort of see why that would be the case there when we did that. So let's restart it here, because now the crest comes up and the ring just moves straight up. But then as the rest of the rope pulls it back down, whoom, it gets sent down and it just sends that pulse right back. So crest comes in, whoom, crest goes back. So that's how a free end works. So let's jump back in here. And here's the picture. So give me my laser pointer. So the incident pulse comes in, and then if it's a crest, then a reflected pulse as a crest goes back out. So a few things, a few characteristics to note about this reflected pulse include, one, just like before, the velocity of the reflected wave is going to be the same as the velocity of the incident wave. And that's because it's in the same medium. It hasn't changed at all. And therefore, the wavelength of the reflected wave is going to be the same as the wavelength of the incident wave over here, same medium. Amplitude, just like before, goes down a little bit. So in a perfect world, they'd be equal to each other, kind of like they're drawn here. But in reality, we'll lose a little bit of energy due to the friction here. And so the energy is related to the amplitude there. You can think about it like how far we stretched, it's like the elastic potential energy. So here's a little animation of a free end coming in, crest comes in, crest goes back out there. Now, what if we have this? What if we have a transmission of a pulse from a less dense to a more dense medium? So let's say this is a lighter string here, and then over here on the blue end, we've got a heavier rope. So when it hits this boundary, it's sort of in between. It's not quite a fixed end. It's not quite a free end. Which is it more like? If you went from a little rope to a big rope, is that more like a fixed end or more like a free end? So it's more like a fixed end. So as this incident pulse comes in, because it's more like a fixed end, it gets inverted, the reflected pulse there. But notice what else happens. Some of the wave is transmitted. So the wave is partially transmitted into the new medium and partially reflected back into the old medium. In the reflected part into the old medium, it follows the rules of a fixed end there. So here's a little animation of it going through there. A few things to note about these pulses. So one is that the velocity of the transmitted wave is less than the velocity of the reflected wave. And that's because, or the incident wave for that matter, that's because this is a more dense material. This material is harder to move around, so it slows down as it enters that material. The other thing is that the wavelength of the transmitted wave is less than the wavelength of the reflected wave, or the incident wave for that matter. And why is that? Well, if it slows down, then the front of the wave doesn't have as far to get before the back of the wave finally catches up to it. So it shortens the wave because its front of it got slowed down. And notice that the velocity and wavelength of the reflected wave didn't change at all. They stayed the same as the incident wave that came in. A couple more things to notice, so let's put the animation back up here, is that both amplitudes decrease. So notice here comes the reflected wave or incident wave, boom. When it reflected, the amplitude went down. And again, that's because the amplitude relates to energy. So the energy is divided between the pulses. This one's going to lose some of its energy, and so that's why it's less. And then this one takes some of that energy away. So some of the energy went away with this part of the wave. What if we did this then? What if we went from a more dense material to a less dense material? Now we're coming from the rope, let's say, to the lighter string. Well, is this more like a free end or more like a fixed end? Well, this big heavy rope is going to easily move that little string, so it's more like a free end. So notice the reflection follows the rules of a free end. We had a crest coming in and a crest gets reflected back here. But just like before, part of the wave is reflected as we can see here and part of the wave is transmitted. And so it continues on this way. So let's look at a little animation of this. Here is a heavier material going into a lighter one. I'll put it back up there again. Let's talk about a few things that we notice here. So a few characteristics of these pulses. One is that the velocity of the transmitted wave is greater than the reflected, or the incident for that matter, because this is a lighter material. It's easier to push around and move through. So the wave speeds up as it comes into the second material. Another thing to notice is the wavelength of the transmitted wave goes up. It's greater than the incident. And this is because it goes faster in here. So the front of the wave has more time to speed away from the back of the wave before it gets in there. So it stretches the wave out there. And then notice that the velocity and wavelength of the incident wave don't change when it's reflected, although we do lose some amplitude there again. And that's because some of the energy left. So again, if you look at the incoming wave, boom, the amplitude goes down because some of the energy went over here. And you may think, oh, this amplitude's even taller. But this material, it's easier, less energy to get it bigger because it's such a light material there. By the way, a good example of this happening is when light hits a window. So when light hits a window, part of it's transmitted and part of it's reflected. You'll see your reflection in the window, but you also clearly light's transmitted through it. In the case of a window and visible light, most of the light goes through, but a small amount of it is reflected back to the other side there.